Hello everyone and welcome back. So now that we have done some data visualization, let's jump to analysis. Okay, we have seen that the interest rate variance depends on our FICO score and loan amount. So we'll be looking at a multivariate linear regression, right? Multivariate linear regression. That means more than one variable affects our interest rate. In this case, FICO score and loan amounts. Okay? So let's start by importing NumPy and Pandas. Okay, so I have already imported some of the libraries and modules that we need. Let's import the others. We'll be using the StatMods library. Okay, this library has a lot of functions for statistical analysis. So let's import that. Import stats models that API as SM. So this stats model has a lot of functions that will help us in statistical analysis. Okay, then we'll import, I think that should be good. If we need to import anything else, we'll import it later on. Okay, so we have our data, right? Our loan.csv file. We have that data, and let me save it in another variable called data frame. Okay, and I'll make 3 separate variables, one for the interest rate, one for the loan amount, and one for the FICO score. Let's do that. Oh, PD is not defined. Let me run. Okay, let's run that. And let's run this again. Okay, so let's make the 3 separate variables. One for our interest rate. So that will be our data frame. And I'll pass interest rate. Okay, one for our loan amount. Let's say loan amount will be our data frame, and we'll pass the loan amount. Loan amount, and finally for our FICO score, right? I'll just name it FICO. Now let me call it FICO score. So we have our data frame. So FICO dot score. Okay. Now what we will do is reshape our data from a Panda series to columns. Okay. That's what we'll do, and for that we'll be using the transpose method. Okay, so we'll transpose our independent variables, which are our FICO score and loan amount, and then we'll transpose our dependent variable, the interest rate. Okay, let's do that. So we'll be using NumPy's transpose method, which is found in the matrix library. Okay, so np that matrix, and then we'll pass what we want to transpose. Let's say interest rate, right? And then we call the transpose method on it, and we'll save that, let's say, in a variable y, y for dependent variable, right? And similarly, let's transpose our two independent variables. Okay, so np that matrix, and then we'll pass the loan amount, and then we'll call the transpose method on it. And let's save this in a variable, x variable. So we have x, and we'll also transpose our FICO score. So np that matrix, and then we pass our FICO score, and we call the transpose method on it. And let's save that in an x variable too. Let me name this one x1 and x2. Okay, so now we have reshaped the data from our panda series to columns. That's what we did for both of our independent variables and for our dependent variable, interest rate. Now let's put our two independent variables, x1 and x2. Let's put those two columns together so that we can create a matrix. Okay, so that will be our input matrix. Let's do that. So np that, I'll introduce a new method. It's called column stack, and this helps us in putting together two columns so that we can create a matrix. Okay, then we'll pass x1 and x2, okay, and I'll save this in a variable called x. So this column underscore stack method takes a sequence of one-dimensional array and then stacks them as columns so that we can make a single two-dimensional array. Okay, now that we have an input matrix, we can create a linear model, and then we can fit that to our data. We'll do that with the add constant method. Okay, we haven't seen the add constant method, but it's one of the the stats models method that helps us add a column to input a data set. Let's see that next. So I call the stats model API SM, that the method name is add constant, and then we pass the x that we created. Okay, the 2D input array. We haven't seen this before, but I want to introduce this now. Okay, so this add constant adds a column to input data set. Okay, and I'll save this in another variable, let's say x. Now we can create our model. Let me name this variable x3. Okay, now we can create our model. Okay, and I'll introduce to you what is known as OLS, ordinary least square. Okay, so we'll base our model on that. It's again also found on inside. It's a function found in the stats library API. Okay, it's called the OLS. Let me write it down. OLS, ordinary least square. What it does is that it takes two array objects like a data frame or array, and then it helps us to perform the regression of the predictor on the response. Okay, so in this case our predictors are the two x variables, FICO score and loan amount. So this OLS takes the two array objects that we created So this x3 and then the y. Okay, so our independent variables, and then this y. It takes those two objects and then it helps us perform the regression of the predictor on the response. So the predictors are this x3 and the responses y, which is the interest rate. Okay, let's do that. So we have the stats module, and then we call the OLS function, and then we pass our response and predictor x3. Okay, so that's our model, and let's save this in a variable called model. Okay, now that we have that, we can fit our model. Okay, let's say model fit. Okay, and then we'll save that. We'll save our fitted model in this variable, model fit. So model dot fit. Okay, good. Now that we have our model, there are certain functions in the stats module library that will help us determine some values. And one such value is called the p-value, the probability value, and the other one is called the r-squared method, which is the coefficient of determination. Okay, let's see those values now. So we can simply print those values. The p values are, then we just call the p values on our model fit. Okay, so model underscore fit dot p values, and then we'll do the same for our r squared value. So print the r squared value is, and then we call the r squared method on our model fit. So model underscore fit that r squared, squared. Okay, so this r squared value, it's called the coefficient of determination, and then it tells us how well the regression line approximates the real data points. Okay, let me write it down. How well the regression line approximates the real data points. Okay, that's what it tells us. And then for the probability function, for the probability value, for the p-value, it has some values, and we want that value to be below 5%, which is, we want it to be between 0 and 0.05. Okay, so that's the convention. You can read more about p-values online, okay, probability value, but basically the convention is that we want our value to be between 0 and 0.05. So if the value is less than 0.05, our model is really good. So if it's close to 0, it's really good. Okay, that's what we want our model to be. Okay, so if that value is greater than or equal to 0.05, which is if it's more than 5%, then we have less confidence in our particular dimension being useful in this model and predicting that it has an effect. Okay, in this case, if it's more than 0.05, that means we are less confident that the loan amount or the FICO score is useful for predicting the interest rate. Okay, let's run the results and see. Oh, and for the R squared value, usually the R squared lies between -1 and 1. Okay, and a good value is if it's close to 1, that's a good value. Okay, and you can read more about R squared online. I just want to touch upon those two. Let's run it and see the result. Okay, from the result we see that the p-values are, okay, we have 3 p-values. So the first one is 0, 0, then the third one is 5.96 times 10 to the power of. So this is a really close to 0 value, right? So this is almost 0 for all of our p-values. And we mentioned that p-values of less than 0.05 are great, and the closer it is to 0, the better it is. So we have really great p-values, and we have an R squared value of 0.66, and the R squared value lies between -1 and 1, and the closer it is to 1, the better it is. So our value is fairly good, right? Okay, so what can this tell us? So what we can summarize is that we have a linear regression model, right? A linear multivariate regression model. Multivariate because of FICO score and loan amount, right? So we have a linear multivariate regression model for our interest rate. And based on this results that we have, we can say that our multivariate regression model for interest rate based on FICO score and the loan amount is described by this values, right? By this model values. So we can summarize that the interest rate is influenced by both loan amounts and FICO score, right? So here we have our interest rate, loan amount, and FICO score, and we reshaped our data to columns, right? We did that for the independent variables, FICO score and loan amount, and for the dependent variable interest rate. And then we put together the two columns so that we can create an input matrix. And we did that by using the column stack method. And this column stack method takes a sequence of one-dimensional array and then stacks them as columns to make a single two-dimensional array. Once we have that, we use the StatModes API's add constant method to add a column to our input data. And then finally, we fit our data by using the OLS method to create a model. And this OLS, ordinary least square. Let me write it down. Ordinary least square. Okay. This OLS takes two array objects like data frames, and then it helps us to perform the regression of some predictor based on what we have. And then we evaluated our model based on the p-values and the r-squared values. Okay, so this is an example of a linear regression. Okay, so go through this project and see what we did. We started with our data and then we formatted it so that it serves us better, and then we visualized our data and then tried to see what other factors affect our interest rate. And then using the scatter matrix plot, we discovered that the FICO score and loan amounts have an impact on interest rate, and we did an analysis on multivariate linear regression. Okay, thank you everyone, and I'll see you at the next lecture.